Hello and welcome to this lecture. We are going to see another type of problem that frequently occurs in the context of parameter estimation. This is of fitting distributions. Okay, so let me get to a particular example. We have seen some examples like this before, but let's get into it. Usually, data when you're doing surveys or some simple computation of data, you use something called a frequency table. So this is an example of a frequency table. The question asks you to fit a Poisson distribution to this data, right? Data given in the form of a frequency table data. What is the data on? It's on something, number of vehicles making a right turn at an intersection over a 3-minute interval. Okay, so what have people done here? They've gone to an intersection and they've counted the number of vehicles making a right turn over a 3-minute interval. Every 3 minutes, how many vehicles made a right turn? Now we repeat it over different 3-minute intervals. Every 3-minute interval you get a number, right? For the first 3 minutes, maybe 5 vehicles crossed, made that turn. In the next 3 minutes, maybe no vehicle made that turn. In the next 3 minutes, maybe 2 vehicles made that turn. In the next 3 minutes, maybe 10 vehicles made that turn. Okay, so likewise you do it for different 3-minute intervals, and you make a count how many. Okay, and you do it for several hundreds of 3-minute intervals. Okay, so in this case, I think there are some 300 of these 3-minute intervals, I think. Okay, so you do that, you get your so many 3-minute intervals data, and then you capture it into a frequency table. So how do you read this? In 14 of the 3-minute intervals in which you observed this, 0 vehicles made the right turn. Okay, in 30 of the 3-minute intervals that you made this observation for, 1 vehicle made this turn, and so on. So for instance, in only 6 of the 3-minute intervals you looked at, 9 vehicles made that right turn. So you get a frequency table like this. Okay, so notice this frequency table is not directly the samples. Okay, the samples are the actual number of observed number of vehicles over all the 3-minute intervals. Okay, the samples, you consolidate the samples into a frequency table. So if you have to look at the samples themselves, how will the samples look? Okay, after some reordering, it may not be in the same ordering as I write it down, but the samples will be 0, 0, how many times? Occurring 14 times, and then 1, 1 occurring how many times? 30 times, and then 2, 2 occurring how many times? 36 times, and so on. Finally, you will have 12 occurring only once. Okay, so this is how the samples would have been. Okay, I'm imagining, what am I imagining? I'm imagining that the number of vehicles making this right turn has a certain distribution. Okay, so let's say x equals number of vehicles making a right turn at that intersection, whatever, in a 3-minute interval. Okay, so this x is my random variable. Okay, it's the random variable that describes some phenomenon of interest to me. Okay, why is this of interest to you? You may generally be interested in the traffic pattern at that intersection, right? So this is one small random variable that describes one aspect of what happens at that intersection. So this is your random variable x. Okay, over a 3-minute interval, you're going to hypothesize that this x has a certain distribution. Okay, some distribution. In this case, we are trying to fit a Poisson, so we are assuming that x is some Poisson lambda. So that's our assumption. Okay, and then what do? I take different 3-minute intervals which I'm going to assume are independent in some sense. Okay, so usually you don't want to keep them contiguous. So you want to say go randomly at one time and observe a 3-minute interval, and then next some other time observe a 3-minute, like that randomly. Okay, so today you can do this in sophisticated ways. If you have GPS data from your Android phones or something, you can get sophisticated ways in which this data can be done even without, in a very non-obtrusive way. Instead of putting people on the thing counting or something, you can get this data in some very clever way. Okay, so let's forget about how you will get it, but this is the distribution. I'm assuming that this x has this distribution, and I have samples, and I'll assume these are IID samples according to x. Okay, so these were observed. I observed so many of values for this x. and I just tabulated them. I tabulated them into a frequency table. Is that okay? So, this is the setting. So, I have samples, I have the distribution, I have to now find the lambda. That is the goal, isn't it? When you fit the Poisson distribution, you have to simply find the lambda. Okay. So, there is a question on confidence intervals. I will come to that a little bit later, but first let us see what is a reasonable way to find lambda. Now, remember lambda is just distribution mean, right? So, for Poisson lambda, lambda is the distribution mean. So, you have to just find the sample mean, right. So, we know that the sample mean is a pretty solid indicator of the distribution mean, and I do not have any prior data or anything to do any simplification on. So, I am just going to assume sample mean equals the distribution mean, and that is a good solid assumption to make. Okay. So, so now I just have to compute the sample mean. If you compute the sample mean, I am done. Okay. So, how do you compute sample mean from frequency data, right? So, sample mean, so lambda hat equals sample mean. Right? We've seen Poisson distribution, right? Maximum likelihood estimate as a sample mean for lambda and all that. I'm just estimating the lambda. Sample mean, I have to add up all these samples and divide by n. Okay. First of all, how many samples do I have? Okay, so let me first start with that question. How many samples? Okay. It is actually 14 plus 30 plus 36 plus so on, right? I have to add up all the frequencies, that many samples I have. That is one thing. And what is the sum of all the samples, right? So, if you want to find the sample mean, you need to know how many samples and then sum of samples. Or how do you sum the samples? It is 14 into 0 plus 30 into 1 plus 36 into 2 plus so on. Okay. So, you have to do these two computations. Okay. So, these two computations are a little bit painful. It is not easy to do. I mean, you need a calculator, you have to add it up and all that. If you do that, you will get it, you will get your sample mean and you will get your estimator finished. Okay. So, simple enough, isn't it? It's not a big complicated calculation we did. We just wrote down the samples in a different way. Just imagine what this question is asking you to do and you can go through and do it. So, this kind of fitting a distribution to observe data, usually presented in the form of a frequency table, is again a very standard textbook problem in this area. You should be comfortable in doing that. Okay. So, let us see if we can do this, and I'll just show you one way in which I like to do these kind of things. So, let us just go to, so usually I like to have a Collab sheet open. So, I have access to all these computational tools. I mean, for this might be a simple enough problem, you do not need a Collab tool and all that, but nevertheless let us just open it up, or if you have a small Python instance running off a terminal, you can use that as well. So, it's okay. So, I like to import NumPy because it's quite useful. Quite often this is good, so you can just run this off first. It will take a little while to connect to some virtual machine and run Python, etc. You can do this on Replit as well, and if you are doing Replit calculations, so Replit is a quick and easy way to do this as well. So, what did I have? I had my frequency data here. I had the frequency. It's good to define it as NumPy arrays. You remember the frequency here: 14, 30, 36, 68. (43, 43, 30, 14, 10). 6411. So, that is your frequency, and then you also need to know the n, isn't it? So, number is basically you can define. So this goes just as a sequence. So for sequences, NumPy has a very comfortable formula. So these two are the two things that we had. Okay, so now that's the thing. So a number of samples now is actually the sum of the frequencies. Okay, isn't it? And then the sample mean, which is sum of number times frequency divided by n, isn't it? So and then you can, if you want, you can print of n and then print sample mean. Okay, so it's a nice thing to just see what these numbers turn out to be. So you see the number of data samples you have is 300 and the sample mean works out to 3.893. Okay, so that's your value here. So I did a quick calculation and this lambda hat works out as 3.893. Okay, not too bad. Okay. Okay, so now let's move on to the confidence interval part. Okay, so we found a lambda hat here, and we are hoping that the the distribution is close to Poisson. So let me make just quick remark on how we can expect this to come out. So supposing you want to add a number here, which let's say is Poisson fit. So how will you go about doing it? You would do e power minus lambda hat times the total number of samples that you had, right? So that would be 300, right? So that would be the Poisson fit number. For this guy, it will be e power minus lambda hat times lambda hat by 1 factorial, whatever, times 300. So it's probability that the Poisson random variable took a value 1 multiplied by 300. Why am I multiplying by 300? Because this is a count over 300 such samples, right? So this many samples we had. For 2 again it will be e power minus lambda hat squared by 2 factorial times 300, so on. You will get these Poisson fit numbers, and these will be reasonably close to this actual frequency that we have seen. Okay, so you can check that also. You can, if you want, you can quickly check in your Collab notebook here. This is just some rough notebook that I've got here. So let me just do this here. So I want Poisson samples, right? So it's good to import so I think I should just first run this again. Okay, so I've imported SciPy stats, and then if you want to compare these values, you can think of Poisson fit as being st dot Poisson dot PMF, and then you put in your values. What is the values? The number, comma, the mean is the sample mean that we have here, right? So that's it. So this would give you the fit, and then you can print it. Multiply, that's just the probabilities. I have to multiply it with 300, or the n, right? So that would give me the actual fit that I expect. So you can see it's coming out as 6, 23, 46, 60, 58, 45, 29, 16, 8, etc. I mean, sort of close enough. It's not really close. Some people will say maybe it's not that Poisson after all, but it's just a fit. It's not expected to be exact. Okay, so this is something that you can do to check. Okay, so now let's move on to the confidence interval. So now the confidence interval is actually a statement about the magnitude of the error that you expect. Okay, so what is typically done here? They've asked you to approximate a normal with the sampling distribution and all that. So let's try and do what this means, right? So first of all, you have to think of the error. error is theta hat minus theta, right? So in this case, if you want, you can write lambda hat minus lambda, because it's after all the we are estimating sample mean here. So this is estimated as the sample mean. Remember, it's a random variable, okay? So it's a random variable, but we know we're going to approximate this random variable lambda hat minus lambda as normal with some mean and some variance, okay? So how do you find the mean? The mean is expected value of the error. It's just expected value of lambda hat minus expected value of lambda. Now this is sample mean. Sample mean's expected value is equal to lambda, so it becomes 0. So it becomes unbiased. So mean is 0. What about the variance? Now what is the variance of the error? So for that, you know, see, since lambda is a constant here, that's the same as variance of lambda hat. So that's the, you know, that's the sample variance, isn't it? So sort of like variance of the sample mean, and variance of the sample mean we know is the distribution mean divided by n, by the number of samples. We know this, but you know, we don't know the value of sigma, right? So we don't know the value of sigma, so we approximate it by the sample variance. So we just take sample variance by n, okay? So we don't know the sigma square, it's sort of difficult to calculate. So we're going to simply take the sample variance and divide it by n to get the, simply equate the sample variance as sigma square. So this is something we've been doing before, we'll just do the same thing here. So here, you know, that calculation, usually we denote it as S squared, right? That's the sample variance. So this is going to be my assumption. This is the normal approximation that we will do, okay? So that's the first step in calculating the confidence interval. So you need to figure out, so we figured out that, you know, the error is going to be normally distributed with mean 0 and some variance, that's actually the sigma squared by n if I can find the actual distribution variance. But since I don't know the distribution variance, I'm going to approximate it with the sample variance divided by n, okay? So this is going to be the idea for variance of error, okay? So if you want a picture, of the PDF of error, so this is our approximate PDF, right? So it's going to be normal, mean 0, and variance is something like this. So this is how it will look. It will look like this, okay? This is a good picture to keep in mind. So what is S squared? Let's see if we can calculate S squared. But remember, now I have to calculate S squared from the frequency table, okay? So how to find S squared from frequency table? That's it's actually quite easy to do. So you can go back and see that, you know, each value occurred 14 times, etc. So your samples themselves are like 0 occurring 14 times, 1 occurring 30 times, etc. So if you're numerically computing it, you have to take care of that. So here is some calculation that I've done here to show you how that would work, okay? So you can see I'm taking the frequency, I'm taking the num which is like 0 to 12, right? Subtracting the sample mean from it, squaring it, okay? And then multiplying by this guy. So maybe I should put some brackets here carefully to make sure things don't go wrong with the bracketing, okay? And then I'm doing a multiplication with with that. So that gives me the you know, the summed up numbers, and then I'm dividing by n, okay? So this gives me the sample variance, okay? So this is my sample variance V. You can print the square root of that just to see, you know, that you're not too far off. The mean is 3.89. For a Poisson distribution, you expect the variance also to be 3.89. So this is coming out as 2.28. So immediately you see maybe Poisson is not the best thing to be fitting here. But anyway, I mean, that's what we are trying to do. So it's not change that around too much. So that's the variance. So this is your well, square root of the variance. If you want to take the variance, you'll get this B. Okay, so now this V by n is going to be my actual variance of the error, right? So I hope I wrote that correctly. So it should be S squared by n. I'm sorry, this is again a mistake. So so this S square is the sample variance, right? So how do you find frequency for S square from the frequency table? I just showed you how to do it. You have to, you know, imagine that 0 occurred 14 times. So you'll do 0 minus sample mean squared times 14 plus 1 minus sample mean squared times whatever 30 or something. You have to keep doing that and add it. Okay, alright. So, we have a handle on the distribution of the error. You assumed it as normal with mean 0 and sample mean by n, sample variance by n as the actual variance of the error. Okay, so that is good. We are in good shape right now. So, now what about confidence interval? Okay, so for confidence interval, what you see is you first find two values. So, supposing you want 95% confidence interval. So, this is the process that you follow. Okay, supposing this is what you want, how do you find the 95% confidence interval? This is what you do, 95. So, first thing you do is 1 minus 0.95 by 2. Okay, so that would come out as 0.05 by 2, that is 0.025. Okay, so I want my error to be within like 95%. What is the probability that my error is in an interval with 95% probability? That is what I want to compute. So, first thing I will compute is I will try to find a delta 1 such that this area probability that the error is greater than delta 1 equals 0.025. Okay, so I want probability that error is greater than delta 1 equals 0.025. So, you find a delta 1 for which this is true. So, basically you keep coming from the right as you keep coming to the left, this area will keep increasing. When it becomes 0.025 you stop. Okay, so that is your delta 1. Likewise, you also find a delta 2 which will in this case be negative, but I will just write it as delta 2 such that this area is also 0.025. So, probability that error is less than delta 2 equals 0.025. So, that is this area. Okay. So, now if this is true, what is the probability of this green guys here? What is the probability of this? Probability that error is less than delta 1 greater than delta 2 is 0.95. Okay. So, with 95% confidence or with probability 0.95, your error is in this interval. So, error being in this interval is called a 95% confidence interval for the error, but usually nobody writes the error like that. So, how they express this is they will say the confidence 95% confidence interval for theta is theta hat minus, so error is between this and that. So, theta hat minus theta is less than delta 1. So, this is greater than this and theta hat, see remember theta hat minus theta is less than delta 1, right. So, that is the thing. So, which implies theta is greater than theta hat minus delta 1 and theta hat minus theta is greater than delta 2, which implies theta is less than theta hat minus delta 2. So, it is between this and this. Remember delta 2 will actually be negative in most cases. So, this will be actually above, this will be below. Okay. So, this is the confidence interval for theta. Okay. So, hopefully this is clear. First, so you need to find the confidence interval, you need two things. First is you need a distribution for the error. Okay. So, usually that translates into distribution for the estimator, okay, because the theta is a constant, and in most cases you are going to make a normal assumptions. If you cannot make a normal assumption, most people use something called a bootstrap. I will talk about it a little bit later. So, you make a normal assumption. So, once you make a normal assumption, you need the mean and variance. For mean, usually you can take 0 or some such value, okay, and for the variance you are going to take the sample variance in most cases, right. So, but variance of the error you remember because it is the variance of the sample mean, it is going to be sample variance which you are approximating by the actual distribution variance you are approximating by the sample variance, you will divide it by n, so that the variance goes down as you keep going with n. So, you get s squared by n as that error. So, that is the distribution for the error. Next is the calculation of the confidence interval itself. So, that involves finding this delta 1 and delta 2. So, this delta 1 is the point beyond which probability of error greater than delta 1 becomes equal to 0.025. Delta 2 is probability of error less than delta 2 is 0.025, okay, and this error you expect to be within delta 2 and delta 1 with probability 0.95, or you are 95% confident about the error falling in this interval. Now, the error falling in that interval translates into theta falling in the interval between theta hat minus delta 1 and theta hat minus delta 2 with 95% confidence. So that's the idea. So if you repeat this sampling over and over again, what does this mean? If you repeat this sampling over and over again, you work with different samples and you use the same thing to find the sample mean, your error is likely to be in this interval with 95% probability. That's the idea behind this. Okay. So how do we find this delta 1 and delta 2 in this particular case? We have already found our distribution variance, or not distribution variance, the sample variance, which we are going to approximate as the distribution variance. That we have done already. We did that just now. So that was 2.279. So that's going to be our guy here. So this we have found to be, okay, let me just change it back to black. This is going to be 2.279 divided by n was 300, right? So that's my distribution for the error. Okay, so that's that guy. So now I need to find this guy, right? Delta 1. How do you find delta 1? So for finding delta 1, probability that error, which is actually normal distribution with mean 0 and variance 2.279 by 300 is greater than delta 1 equals 0.025. Okay. So this usually we have to convert it into a statement about the CDF of the normal distribution. So this is just a standard problem in probability, right? You've done so many problems like this. How do you calculate probability of an interval for a normal distribution, but it is inverted. Okay, instead of asking you for a probability for delta 1, you are asking given delta 1 you can find this probability, but you're given probability, how do you find the delta 1? So it's sort of like the inverse CDF problem. It's not directly the CDF problem. How do you do these kind of things? So this is the same as, see now, greater than delta 1 is same as 1 minus probability of this same guy being less than or equal to delta 1. So this is the same as probability of a normally distributed random variable with mean 0 and variance 2.279 by 300 is less than or equal to delta 1 being equal to 0.975. Okay. There is a similar statement for delta 2 you can make. Delta 2 is also probability that a normal distributed random variable 0, 2.279 by 300 is less than or equal to delta 2 equals 0.025. Okay. So these are two inverse CDF problems, because this is the CDF value, right? CDF of this normal distribution has to be equal to 0.975. CDF of this normal distribution has to be equal to 0.025. Okay. So how do you do this calculation? This is not a very difficult calculation to do. One can, this guy. So what you do normally, this is something that I would do for finding lambda 1. There is this function in SciPy stats for normal PPF, it's called. Okay. You can put in a value which is 0.975, comma, and you can give arguments which is mean 0 and the variances, and scale is, it needs to be sigma, so square root of the variance. So np dot sqrt of v by 300. Okay. So that's L1, and for L2 it's the same thing, except we are going to do 0.025. Okay, so we can print these two guys just to make sure we have not done anything crazy. Okay. Oh, V is not defined. I didn't run this. Okay. Okay. So this is okay. This sort of makes sense. 0.25 on one side minus 0.25 on the other side. So this is not too bad. It's quite reasonable. Okay. Okay. So this is my delta 1 and delta 2. Notice that the normal distribution is symmetric. So since the normal distribution is symmetric, delta 1 and delta 2 will be minus delta 1. Okay. Okay, so that's to be expected. So from the calculations, you're saying that delta 1 equals 0.25 roughly, delta 2 is minus 0.25. So you can get your confidence interval. So your theta hat was 3.83. So it's the confidence interval for 95% is 3.83 minus 0.25 and 3.83 plus 0.25. So the confidence interval will work out to so maybe I should write it out here, 95% confidence interval is 3.83 minus 0.25 comma 3.83 plus 0.25. Okay, so that's the way these confidence intervals problems are worked out. I did this in some more detail just to show you how this happens. So this is again a basic skill that you should have. Given a frequency table, if you want to target a certain particular distribution as a fit, you should be able to compute the parameters that are involved in the distribution. In this case, it was just the mean. We could compute it as the sample mean. Not only that, you should be able to provide a an idea of the 95% confidence interval, so some sort of measure for how confident you are about the answer. Okay, so that was one fit. If you're going to do one more fit, this is a geometric distribution fit. Once again, we have the most of the things worked out, but I just want to show you once more how to do it, and we're going to use a normal approximation, 95% confidence interval, exact same thing. Maybe we'll do this a bit quicker, but it's going to be the same thing. Okay, so once again, remember this is some number of hops between flight of birds. This is again frequency data, number and frequency. So the number 1 occurred 48 times. So again, you should think of the x as being geometric p. Okay, p is unknown, we have to find it, and the samples are 1 occurring 48 times, like that, right? So 2 occurring 31 times, like that. So you can think of this like this. These are IID according to x. How do you find p? Okay, so you can do the ML estimate. For instance, p hat is going to be n by x1 plus xn. Okay, how do you find each of these things? N is actually the sum of all the frequencies, right? How do you find from the frequency table? You add up all these things. I believe the answer will come out to be something, and then you divide by the sum of all these things, which is frequency times number. Okay, so let's do this. This is not very hard once again. So we'll do this once again in our rough work here. Number now is np dot a range of 1, 13. So this will give you the numbers from 1 to 12, and frequency I have to find now. Okay, 48, 31, 29. Six, 5, 4, 2, 1, 1, 2, 1. There you go. That's the number that we've got for the frequency. Okay, so these two one can run, and then these things are just the same, right? So you have the sum, and then this is just sample mean. So we can just do this. You can find an n, which is np dot sum of frequency times number. No, sum of frequency alone. Okay, that we know. And then the sample mean is not what we want. I want p hat, which is going to be n divided by np dot sum of this is frequency times number. Okay, so we can print n and also print p hat. All right, let's run this. There you go. 130 is the number of samples, and 0.3581 is the estimate for p hat. Okay, so that's good enough. That's good. So it works out as 0.35 something. Okay. What about the confidence interval? You've been asked to make a normal approximation. The problem with this now is you're going to have a p hat, and then there's going to be a p, isn't it? So So what do you do with this? Because previously we had sample mean and we could estimate the distribution quite easily, but now we don't have that. But so let's see how to go about doing this. So I'm going to assume p hat minus p. So when we do the confidence interval, now there's going to be one difficulty. So let me point you to what this will be. Okay, so we have a p hat to be n by x1 plus this. The problem is, supposing you take error to be p hat minus p, and supposing you want to do a normal approximation. Let's say you want to say it's normal, but there's a mean and there's a variance to be established here. What do we do for the mean? So if you start looking at the expected value of error, hoping that maybe it's unbiased, so it becomes 0, you will run into this difficulty. So you'll have expected value of p minus p, and then you will have to compute this humongous quantity, which is very, very difficult. There's no easy closed form for it, and you'll run into this difficulty. Okay. So whenever we run into a difficulty where there's an expected value calculation or probability calculation which is too difficult, we will end up relying on Monte Carlo simulations. Okay. So this is something that is done all the time. It's called Bootstrap. Okay. So this is the name for it. Bootstrap is what you do when you cannot calculate an expected value like this. Given the distribution assumptions, it seems too confusing. So you just do Bootstrap. So what do you do Bootstrap? What is Bootstrap? So we had a value for p hat, right? P hat ended up being 0.35. Okay. So what you do is you generate IID samples according to geometric 0.35, whatever it is that you had as the p hat that you calculated from one samples. You keep one sampling, you calculated this, you do this, so you repeat, you find some capital N samplings. Okay. So you repeat, this is like Monte Carlo. Okay. So you do capital N such samplings. Okay. So what does that mean? So you will have the first sampling will be x1, x2 something, xn. So you'll use the same n. N was what, 130, right? Keep that in mind. So you use the same n. So capital N could be some 1000. Okay. You do the first sampling, you do the second sampling, you will get another set of samples, right? So maybe I should call it x11, x12, x1n, x21, x22, x2n, right? From here you find a p hat 1, you find a p hat 2, like that. You will have p hat 1000. Okay. So these, because all of these guys are independent, these are like samples of p hat. Okay. So you treat these as samples of p hat. So if you want to find expected value of p hat, so expected value of p hat is a good approximation is p1 hat plus p1000 hat divided by 1000, things like that. So you just think of these as samples and you use whatever you want to do from here. So this is called the Bootstrap. So let's do the Bootstrap now. We'll do it very quick with our wonderful little notebook that we have here. So let's go here. I'm going to do a little Bootstrap here. So I need this capital N to be 1000, and I have a small n which is already there. It's 130. That's okay. So then I can have a loop which goes from 0 to n, right? For every time in the loop, I need to generate my samples, which are going to be st geometric dot rvs of p hat, right? So p hat, which is 0.358 in this sense, and size you can put equal to small n. Okay. And then what is my p hat I? This is let's just do this. This is, we'll just say p hat Bootstrap is np dot zeros of n, okay, p hat boot of I equals, just the average, it's actually n by np dot sum of xi, right? So that's so every time we generate this many numbers and then this many geometric random variables, and you keep doing the average along with that, so you get your p hat boot of I, okay? And then now how do I find, supposing you want to find the bias from Bootstrap is just, np dot average of p hat boot minus p hat. So one can do this. You can print the bias and see, just to see that you get something reasonable. This will run reasonably fast. You'll get the answer. So you see the bias is quite small. In fact, you can go a little bit further and plot the histogram for the p hat boot. For instance, I will leave that as an exercise to you, but you see the bias is this small. So you have an estimate for the bias. It's 0.003088. Okay, this estimate I will use just like that for my number here. Okay, so this is called the Bootstrap method. So what was it exactly? 0.00309. I'll take it as. That's that. So what do I do for the variance? You can argue in, you could continue with the Bootstrap, for instance, and find the variance. That's not wrong. It's something we can do. So if you have to continue with the Bootstrap for the variance, you could do it, or you could find sample mean or various other things like that. But once we have done Bootstrap, why not do Bootstrap over and over again? So we want to find variance of the thing. So I'm going to just subtract p hat boot minus p hat, or just give the variance. That should be it, I think. So variance of the Bootstrap is np dot. I think I can do. There's this subtlety with biased versus unbiased variance, which will give you what you want. Okay, so that's good. So p hat boot, right? So this will give you the variance of p hat, which is the same as the variance of the error. So as far as we are concerned, we can do this. We can just put the DDOF equal to 1 if you want something slightly better. So you can print once again np.sqrt of variance boot. This gives you a sense of the sigma value, right? Okay. So you got a slightly different value here. So this is what happens when you do simulations, right? You run it once again, your bias value changes, your this value changes. So that's the danger of this Bootstrap method. So you just take some value, you hope that it's close enough to look at the range of the values of this. So maybe this 1000 is not a good enough number. Maybe one needs 10,000, right? So just to be very, very sure. So you get some value here, and then hopefully it doesn't vary too much. Yeah, it doesn't vary too much. So we can take 0.002 to be a reasonable estimate, I think, for this. So hopefully you see this. So this is one of the problems with the Bootstrap method. So you keep doing more and more, you get more and more different values. So which one do you take? So at least the variance seems to be quite stable, 0.025, but the bias seems to sort of keep varying a little bit more than we would like. So maybe we can take something reasonable in that range. You're not going to be too far off if you want to calculate it. Okay. All right. Anyway, so that's the calculation. It's the sigma value in some sense. It's 0.025 by so n was 130, right? So it's going to be this guy squared by 130. So that was the sigma value, and this one maybe 0.003 is too much. We can take 0.002. That seems to be a reasonable estimate for the mean and the variance. So notice what I did for both the mean and the variance. I had to use the bootstrap method, because this one the estimator is like n by the random variable. You're not going to be able to find expected value, so you do bootstrap for this. Okay, so this is how you use bootstrap. Once you found this distribution, calculation for the confidence interval is the same as before. I'm not going to repeat it for you. No, there is a small bias 0.002, so it won't be symmetric. So delta 1 and delta 2 will not be exactly equal. There will be one small difference here, but you can do this exactly like we did before. Okay, so I'm not going to go into great detail here. So we'll leave it at that point. Okay, so hopefully you saw a reasonable experience with these kind of problems. When a frequency table is given to you, how do you fit a particular distribution to that? Okay, it could be different distributions, and how do you find confidence intervals for your what you estimated? There could be different distributions. In some distributions, everything might be simple. You can find out confidence intervals without too much trouble. But in some cases, you won't be able to easily get nice expressions for bias and variance and all that, and you have to rely on Bootstrap. And we saw the problem with Bootstrap, right? Every time you run, you may get different values. So you have to do it long enough time so that you get reasonable numbers, and you can be quite confident about the answers you're getting. Okay, so that's the fitting the distribution. The last example I wanted to do was a discrete distribution. So here also you will get an interesting thing. So in this case, we again have a frequency table, but the distribution is not continuous or anything like that. It's a discrete distribution, and we have to find the ML estimate for theta. Once again, how do you read this data? It's a discrete random variable. It's from genetic experiment, goes back a few years. There are four values. So the way to read the samples here is samples are 1, 1, 1 occurring 1997 times, and then 2 occurring 906 times, like that. Okay, so that's how you read the samples. Okay, and the distribution is here. This is the distribution for x. Okay, PMF for x. Okay, so you can use the method of moments. It's quite simple, but this what's been asked here is the ML estimate. So how do you do ML estimate here? ML estimate is again likelihood. How do you do the likelihood here? It's going to be 1 by 4, 2 plus theta raised to the power 1997, okay, times 1 by 4, 1 minus theta raised to the power 906, 1 by 4, 1 minus theta raised to the power 904, and 1 by 4 theta raised to the power 32. Okay, so you can take log and then you can differentiate, etc. So let's do that. Log L, you will get some constant here. So I like to just write it as a constant, like log of 1 by 4 power 1997, 1 by 4 power. So 1 by 4 power, the total sum that will come there, and that's a constant. It doesn't matter to me. What really matters is 1997 log 2 plus theta plus 906 plus 904. So 906 plus 904 is 1810, right? So 1810 log 1 minus theta plus 32 log theta. Okay, so now I'm going to differentiate and equate to 0. So I'll get 1997 by 2 plus theta minus, what did I get minus? Because there is a 1 minus theta, right? So 1810 by 1 minus theta plus 32 by theta equal to 0. So if you rewrite this, this will give you a quadratic equation. Okay, and you can solve for this quadratic equation and you will get your theta hat. Okay, your quadratic equation may have two values. Only one of the values will be between 0 and 1. Okay, the value of theta is known to be between 0 and 1. Okay, so it has to be between 0 and 1 because it has to be positive, because otherwise 0.25 theta will go negative, and it has to be less than 1 because otherwise 1 minus theta will go negative. Okay, so you see theta is between 0 and 1. So you use that and you find your approximate actual solution for this quadratic equation. Okay, so I'm not going to go ahead and complete this problem for you. I will leave the solution of the quadratic equation as an exercise. Go ahead, convert this into a quadratic equation. How did I know it will be a quadratic? Think about it, right? So you can simplify this, you will get a quadratic equation, and you can solve the quadratic equation, you will get the answer. Okay, so notice how easy it was to write this down and do it. Given a frequency table, how to do estimation of parameters and fit a certain expected distribution to it is another very simple and nice type of technical problem that you can do. You can also do confidence intervals for this theta, by the way. Yeah? You can do a distribution for the theta hat, maybe using some bootstrap, this, that, etc. So how would you do confidence intervals is again an interesting question in this case. I will leave that open for discussion if you are interested in it. Okay, thank you very much.